Okay, we're back to talk about measurement, error, and uncertainty. And while these topics don't always, or even really typically come up on the Regents, they are important to know about if you are planning on any sort of career doing the sciences. And even if you're just taking a science class, you should understand what they are. And even if you don't plan on doing anything with science in your life, you should be scientifically literate. So knowing how to properly measure things, knowing what error really means, knowing what uncertainty is, those are key topics. How long is this box right here in centimeters? Well, I have a protractor right here. I'm going to line this up. The centimeter markings are along the inside of the arc here, or this line. So I'm going to line it up with the edge, and I'm going to measure. And I'm going to say that comes out to about, I'm going to say it's between 6.8 and 6.9. I'm going to call it 6.86 centimeters. Now you might be saying, well, what if I just wanted to say 6.9? Or what if I just wanted to say 7? Well, those aren't really correct answers for how we're going to measure things, okay? It would have to be in this format. I'm not saying it has to be this number. 6.80 would probably be acceptable, 6.81, 6.82, 6.83, and so on and so forth, all the way up to 6.90. I would accept any of those answers, okay, because it follows a certain format. I know it's got to be between 6.8 and 6.9, but you'll notice that on my protractor, there are markings, and we can see that the numbers are, for centimeters, 1, 2, 3, 4, 5, and so on. The smaller lines are millimeter markings. So that would be 1/10 of a centimeter. That's this place right here. When you're measuring things, and this is actually the same as on a typical meter stick. Let me go show you, get you a meter stick for you. A meter stick also has the smallest lines being millimeter lines. Okay, here's the end of a meter stick, and you can see that there are, okay, so 3, 4, and then there's 10 lines in between. Those are millimeter markings. So always remember that on a meter stick, the smallest lines indicate millimeters. The numbered lines indicate centimeters. Okay? So what this means is that when you're measuring something with a meter stick or with our protractor right here, when you measure, you always estimate to the nearest 1/10 of the smallest marking. So on this protractor and on the meter stick, we estimate to the nearest 1/10 of a millimeter. Now that might sound kind of funny, 1/10 of a millimeter, what does that mean? Well, if this is the millimeter spot, okay, because a millimeter is 1/10 of a centimeter, if we need to estimate to the nearest 1/10 past that, that means we need another decimal here. So if you want to say 6.83, that's fine. 6.88, that's fine. In this case, given this particular measuring tool, we always estimate one place farther than the smallest markings. So if the smallest markings are millimeters, we estimate to the 1/10 of a millimeter, one place past that. The reason we do that, or one of the reasons that we do that, is so we can be as precise as possible. No measurement that you make will ever be perfect. Measuring tools are imperfect. Think about it. There's nothing that's exactly 1 meter long, except whatever is defined as a meter. But for any meter stick that you might see in this classroom, you can't tell if it's just a little bit short or a little bit long. No measurement tool is ever going to be exactly perfect, okay? And this idea that nothing you measure with is ever going to be perfect is known as measurement uncertainty. Measurement uncertainty. And again, that is just the idea that no measurement is ever perfect and all measuring tools have some level of uncertainty with them. Measurement uncertainty falls into a category of what we call errors. You guys are used to talking about error as something wrong. Oh, you committed an error. In baseball, there are errors. You made an error on your homework. That's not really what error means in science. Error does not mean that you did something wrong. Error just means, well, it's kind of a category of different ways that your answer might not be perfect. Okay? Measurement uncertainty is one type of error. It's the idea that no measuring tool will ever be perfect. There's no way to tell exactly how big or heavy something is. However, we do the best that we can. In addition to giving our best guess, we give a range. And this can be a little confusing, known as the uncertainty that the true measurement is likely within. So for this box, if we were writing our answer, our best guess answer, with an uncertainty, we would write it like this. 6.86 plus or minus 0.01 centimeters. This plus 0.01 is the uncertainty. Basically what we're saying here is that 6.86 is our best guess, our best estimate as to what the true value is. However, we're acknowledging that due to measurement uncertainty and some other stuff we're going to talk about, 6.86 probably isn't exactly the right answer. However, we are reasonably sure that the answer falls either within a range of either above or below this number by 0.01. And if you think about it, above or below that number by 0.01 would mean that the range that we're fairly confident the true answer is within is 6.85 to 6.87, okay? So this right here shows us the range that we're fairly confident our answer is within. This is our best guess as to what the true value is, even though there's no way of really knowing what that true value is. So we have measurement uncertainty. That's more of a concept than anything. It's the idea that no measurement is ever perfect. And then when we actually do make a measurement, we call this part the uncertainty. So how do I know how big the uncertainty is? There's some rules down here. In general, for non-digital instruments, that means things that you have to actually read yourself, that don't just give you a number like this. You actually have to read yourself. An example of a digital instrument would be, I think this one works. Let's see here. Yes, an example of a digital instrument would be like this stopwatch right here. It just tells you the time. So, for non-digital instruments, the uncertainty is always 1/10 of the smallest gradation or marking on the instrument. So again, the smallest markings on here are millimeters. The uncertainty must be 1/10 of a millimeter. That comes out to, if it's 1/10 of a millimeter, 0.01 centimeters. Okay? For a digital instrument like this, the uncertainty is instead half of the last digit place. So for example, this shows right here 1.35 seconds. The uncertainty on this would be 0.005. The last digit place on this, the last place that you can have is 0.01. Half of that is 0.005. So if this was a time for something, I would write down that the measurement and its uncertainty would be 1.35 plus or minus 0.005 seconds. Okay? Those rules go for any instrument. So just to recap, when we measure things, we always measure them. If we're reading something on a non-digital instrument, we measure to the nearest tenth of the smallest markings. We measure to the nearest tenth, or we measure, I guess I should say, let me back up. We measure one place beyond the smallest markings. So since this has millimeter lines on it, that means we measure to the nearest tenth of a millimeter. For talking about the uncertainty, the size of the range in which we think the true answer is within. For non-digital instruments, it's the same thing. It's 1/10 of the smallest marking on the instrument, so that means our uncertainty for this protractor is 0.01 centimeters. For digital instruments, the uncertainty is just half of whatever the last place is. Last place on this is 100th of a second. It doesn't matter if there's a 5 in there, it's just the place value, it's just the place. So the place is 100th. How do you take half of 100th? 0.01 divided in half by 2. 0.005 would be the uncertainty. If we were doing this in class, I would now have everyone grab meter sticks and we'd all measure the length of the floor tile and we'd record it with uncertainty. And I would make sure that you get the format right. If you're reading a meter sticks have their smallest markings to be millimeters, which is basically 1/10 of a centimeter. So you need to estimate one place past that and include the uncertainty. So a possible value would be this, 30.50 plus or minus 0.01 centimeters. Okay? Now, If I asked a bunch of people this question, I would get many variations on this. Some people would say 30.60, some people would say 30.55, some people would say 30.30. But we all basically measure the same thing. These tiles in my room are all the same size. Not everyone will get the exact same answer, and that is absolutely fine. That's just another type of error. It is known as random error. A way to think about random error is it is the natural spreading of data around a value. If everyone in this class all measures the same thing, we're all going to get different answers. That doesn't mean any one person necessarily is right or wrong. It's natural. People are going to read things slightly differently. They might have the meter stick lined up slightly differently. That's not necessarily wrong. It's just something that is always going to be unavoidable. Even if you have the best scientists in the world using the most precise instruments, you will still get some random error. It's impossible to get the same exact thing every single time. There are just too many little factors that you might be unable to account for. However, we want to minimize random error. We don't want a lot of spread around the data. We accept that some will exist, some spreading of the data, but we don't want a lot of it. So the idea here is that it's unavoidable to have some random error. You didn't do anything wrong. We want to reduce how much spreading there is of the data. In order to reduce the spreading of the data, you do multiple trials. This ensures that even though by doing more trials you'll probably get some spread, you still get all of the, you're reinforcing the idea, most of your measurements will be fairly close to the right answer, or to the quote unquote true value of this. So that's why when we do this activity in class and you all measure a floor tile, there are some outliers, but having more trials or more people measuring just means that our data is going to be seemingly more precise, more closely grouped together. And that means that we value it a little bit more. Okay, so multiple trials reduces random error, it reduces the overall spread, because you'll probably have more data points that are closer to, quote unquote, the accepted value. So far we've talked about measurement uncertainty, the idea that no measurement is ever perfect, and the idea that random error, and the idea of random error, which is the idea that if you take multiple data points for the same thing, you're never going to get the same answer all the time. You're going to have some spreading of the data. Both of those will occur in any experiment, okay? Our job is to limit those types of errors by using the most precise tools possible and by taking lots of data points. We're always going to have measurement uncertainty and random error, but we try to minimize their effects. On the other hand, there are two other types of errors that are much worse than measurement or instrument uncertainty and random error. The first one is the worst of all, and it is called human error. You might have heard of human error before. You might have even used it as an excuse in some lab activities. Human error is any sort of error that is easily corrected by using common sense, following the lab procedure, and paying very close attention to what you're doing. Some common examples of human error include the following: making a math error. Everyone makes math errors, but it's your job to correct them, okay? It's not my job to point them out to you. It's not your job to say, oh, I didn't get a good value for this experiment because I did some math errors. Well, then go fix them, okay? If you think you made a math error, go and check. It's not my job to check for you. It's my job to grade your math and make sure that it's right. But that's a type of human error that's not acceptable. Using the equipment wrong. There's a difference between using equipment wrong and having faulty equipment. Using equipment wrong means that you're not paying attention to what you're doing, or you're using it in a way that is not approved or not what you're supposed to be doing. That's human error, okay? If you're knowingly doing something wrong, if it's more than just a simple mistake, that is human error. I see people say this all the time. It's kind of similar to a math error. If we're timing something with our stopwatch, people say, well, part of the error was I wasn't accurate with my stopwatch. Well, then what were you doing? You should do it again if you don't think you were accurate with your stopwatch. Your times and your measurements should be as good as you can possibly make them. Now, that doesn't mean that you sit there and you try and make it absolutely perfect and you take 30 minutes to take a data point. It means focus on what you're doing, take the data point to your best of your ability and move on. You have to pay attention. I see people all the time saying, oh, I wasn't accurate with my stopwatch. Can you ever be perfectly accurate? Humans are not very good at using stopwatches in general unless you've been trained. So unless you are just not even paying attention to what you're supposed to be timing, you're not going to be perfectly accurate with your stopwatch. That's not an acceptable that's not an acceptable error, okay? That's included in measurement uncertainty. That is not an acceptable method or a reason that an experiment didn't go right, okay? On labs, I will often ask you this question. I'll often ask you for ways to correct error. What were some sources of error is usually the way I put it. What are sources of error in this lab? So when asked for ways to correct error on a lab, saying human error, I'll correct the human errors, is never acceptable. You are never allowed to say this. Why? Because you should have corrected that while you were doing the lab itself. Not now that the lab is done, you're like, oh, I didn't do that good. I guess I had a lot of human error. No, pay attention during the lab and correct it yourself. Okay? Human error is unacceptable as a reason for why something didn't work. All right? So human error, it's just basically you're not doing a good job at science. Not that you're incapable of doing a good job at science, but that you are deliberately not putting forth your best effort, basically. The second type of bad error that we want to completely eliminate is known as systematic error, and people sometimes have trouble differentiating this from human error. The difference here is in that human error you should be able to avoid. Okay, human error is bad. Systematic error are mistakes, okay? You didn't intend for them to happen. It was just something that maybe you didn't think about, or maybe you didn't realize that the equipment was faulty somehow. Systematic error is not necessarily a reflection on you not having common sense or doing something wrong. Systematic error is, oh, I didn't think about that. Systematic error can arise from flawed assumptions or procedures. In other words, you're assuming something that is correct that's not correct. You're assuming something that isn't correct but is. If your procedure has a mistake in it, not like a lazy, careless mistake, but something you just genuinely did not think of, or sometimes you can have faulty measuring equipment. What happens when you have systematic error is that all of your data gets shifted. What I mean by that, imagine that you had a meter stick, and by the way, all of my meter sticks are close enough to a meter so that this isn't really a source of error that I want you saying. Imagine that you had a meter stick, and the meter stick, at the meter stick factory or wherever they make meter sticks, it was accidentally printed on a length of wood that is actually a yard long, not a meter. We just talked about recently how a yard and a meter are slightly different. A meter is longer than a yard. So imagine you had the meter markings accidentally squished onto a yardstick. If you tried to measure the length of something, let's say you measured it to be 20 meters, well, you really measured it to be 20 yards unbeknownst to you. The object is really shorter than that in meters because basically you used a smaller meter and measured 20 of them. Really, it's probably like 18 or so meters. So that is an example of a systematic error. Every time you would measure with that meter stick, it shifts your data so that things that are smaller than a meter appear to be a meter in length. So that's an example of a systematic error. Your meter stick isn't exactly a meter. Another one that arises sometimes is anticipating something happening, especially with a stopwatch. A lot of times people will, with a stopwatch, they'll anticipate that the object is about to hit the ground, and so they'll try and stop it, and they'll stop it too quick. Well, that'll shorten the time that you record. It'll make the time shorter than it actually was. And a lot of times people will think that they're late with starting a stopwatch, so they'll try and stop it right on time. That doesn't really make sense. If you start late and stop early, you're going to measure a time that's much smaller than it should be. So anticipating something happening is another type of systematic error, if you can tell that you're anticipating something. The key is to not anticipate. If you're going to start your stopwatch late, you got to end it late, okay? Not really late, but just a little bit late. One key for this is if you're, let's say you're dropping something and you're waiting for it to fall and you're timing this, have the person who's timing not look at the object that's falling. Have the person that's dropping it say go or drop, and then when the person hears that, start the stopwatch, and then they listen for when the object hits the ground, and then they stop the stopwatch. That's a good way to avoid anticipation, because even though you'll be starting your stopwatch a little bit late, you'll also be ending it a little bit late. And a third one, which you've probably heard of before, and probably done before, another systematic error, is not zeroing out a scale. Not making sure that the scale, let's say you're measuring the mass of something, not making sure that the scale has nothing on it or set points to 0 while there's nothing on it before putting an object on it. That will shift your mass one way or another, okay? All right, that is everything I want to talk about with error. Next video, we'll talk about percent error, a calculation, and the terms accuracy and precision.